Our last speaker from the University of Wisconsin is Professor Lisa Everett. And please, Professor, you're listening.
Yes, thank you very much. I very much appreciate the opportunity to be here today. I'm going to discuss some recent work that I've done with my former postdoc and students on what I call lepton flavor portal matter, so in the realm of particle physics. And okay, let's get started. So what I should probably do is, hold on, let me go to my PDF and try to make it into a slideshow so that I can just scroll. Okay, maybe I'll just scroll. So first, I'd like to just say a couple words about Durmuş. I'm sorry I can't be there with you today. I couldn't be there in the room to hear about everybody's talks and celebration of Durmuş. He was amazing, brilliant physicist, extremely impactful, and extraordinarily broad in his research efforts. I've always been very much inspired by him. Um, he was one of my very first mentors in my career as a physicist. We met back in the mid 90s at the University of Pennsylvania. He was a postdoc there, and I was a PhD student just beginning and wondering if I was in over my head in high energy theory. He was the first mentor I had, um, helped me learn. We worked together. My first paper was with him. In fact, I remember he had to leave before we put that paper on the archive because he had to go into the military to do the military service. And so part of what I needed to do was to make sure that all the work that he had done, if we needed to do more scans or whatever, that I could do those things. So he instructed me most helpfully and openly. Um, and I also remember mentioning that I remember the day when he came out of the military service because if you go back to 1998, I'm forgetting the month at the moment, but if you look him up, you'll see there's a certain time frame where I think he came back and there were something like order 10 papers on the archive of Hep PH that he submitted just after he returned. It was really exciting and wonderful to see. Um, anyway, it's such an honor to be here to speak today in celebration of Durmuş. So Durmuş was very passionate about physics, as we know, and our field has had lots of interesting progress over the past 30 plus years. And I would say among the many exciting developments that we've had is the story of dark matter and our thoughts about it today. In particular, there's been a recent huge renaissance of ideas in this domain. There's always been some rather broad set of possible dark matter candidates over the years, but in recent times, I would say a lot of entries in the energy spectrum have been filled out. A lot of focus in areas that maybe hadn't been as strongly focused on in previous decades. I've put here the standard, image that we all use, and this isn't even complete. There's also super heavy possibilities for dark matter. And so among these, as a particle physicist myself, I'm always interested in the potential particle physics connections with dark matter. And for today, we're going to focus on the well-known dark sector paradigm, which has light dark matter and light mediators. So it's the usual kind of story. There's posited to be some sort of dark sector where there's no standard model gauge charges. Instead, there could be a dark sector gauge group. There's some fields in there, including what a dark matter candidate could be a fermion, could be a boson. And then there's some mediator or portal is the phraseology these days for how the dark sector communicates with the standard model sector. And it obviously has to be done in some way to keep the interactions weak of the dark matter. And there are many possible portals. There's been lots and huge amounts of work on this. I've cited some reviews above. Here, I'm going to consider a very standard framework, one of the probably the most well explored, which is to have a gauge boson vector portal, a abelian one, so U1, and it's based on the portal aspect is kinetic mixing with the standard model hypercharge. So in these vector portal kinetic mixing models, about which there's a very large literature, we've got some dark gauge group. There's a U1 dark symmetry that's part of that gauge group, a dark matter field. And then there's a kinetic mixing portal, which has some dark photon coupling to the standard model. So, and that coupling is going to be proportional to some epsilon, that's the kinetic mixing parameter in this framework. And you get the correct dark matter relic abundance for some range of parameters where essentially what you have is GeV or 10th of a GeV, and the epsilon kinetic mixing parameter is 10 to the minus 3 to 10 to the minus 5. And so the model building framework might be the origin of this parameter. So it could be you have some very high scale theory and it's some input from that. But one can also imagine scenarios, and this is a very old story. Hold'em 1986 is the famous paper on this type of idea, that suppose you have a situation where this thing is loop generated just via new heavy states, then you can easily calculate this loop and you see you've got this essentially mixed trace coming in there with some weighting of the various particle states running inside the loop. And if the mixed trace of the hypercharge and the U1 dark charge is equal to 0 over those states, then what you have is a situation where this epsilon is not only a finite parameter, it's also a calculable parameter. And so what I'm interested in is to think about those possible states that are in the loop. Let's assume that they're fermions. They're going to be charged under both the standard model and the dark gauge group. And these are taking the name of what's called portal matter, broadly speaking. And there's various requirements on what this portal matter might need to look like. First of all, it's pretty clear that these states, if they exist, would have to be vector-like with respect to both the standard model gauge group and the U1 dark gauge group. This has to do with the fact that we've got anomaly constraints on these theories. It also has to do with the fact that we've got direct search constraints and precision electroweak constraints that are particularly Higgs coupling constraints, particularly stringent with regards to chiral extra generation. So we want vector-like ones. And because we want some hope to try to see it, for example, at some current or future collider, we want these things to mix with the standard model. So they should have the same standard model quantum numbers as some standard model field. So it could be quarks or leptons, but it should be something which has the same quantum numbers. So there's some possibility that one of them in the pair can mix with the corresponding standard model particle. And it's well known that such situations actually leads to quite distinctive collider signatures for after you produce these types of things. Since these particles would have standard model charges, you can produce them at various experiments, and then they're going to decay. And what's interesting about them, as compared to quote unquote ordinary or standard vector-like quarks or vector-like leptons, instead of decaying to a lighter fermion and a standard model fermion and a electroweak gauge boson, say, they're going to decay to a highly boosted standard model fermion or jet, along with a dark photon or dark Higgs, so the dark part. And the bounds are quite different in this case. And this has been quite reasonably well explored, especially by Tom Rizzo, has many papers on this type of subject about the collider reach for these types of particles. So that's the setup. And what I'm going to focus on here is the case where this portal matter has lepton type charges. So they could be they could look like lepton doublets of the standard model, just now they'd be a vector-like pair of them. So there'd be a left and a right-handed doublet under SU2, or they could be the charged lepton singlet analogy, similarly, again, in the vector-like pair combination. And I'm going to talk about, hopefully, 3 different works that we recently did on this topic. There's a 4th in preparation that I won't have time to get into now. The first one was when we were first playing around with this a couple of years ago. What we were interested in to see was whether or not in this sort of, dark photon type models, that whether you could have a lepton portal matter scenario that could accommodate the G-2, assuming, of course, that this is actually the discrepancy that may be there between theory and experiment is actually a real discrepancy and doesn't have to do with, for example, theory prediction corrections that would need to be fully understood that people are actively working on. So in this case, we'll see that we can do this. And in fact, the effect is completely insensitive to any details of what the dark matter is, et cetera. So it's quite universal as long as you have a certain set of portal matter content with certain types of couplings, and it has to talk only to the muon. Okay. And that's this aspect of what we're calling lepton flavor portal matter is that it would need to couple preferentially to muon and not to others. So that led us also to think about trying to implement such a toy model into a broader framework. And so we tried to look for a theory with a non-abelian dark gauge group, where that dark gauge group breaks down to the U1 dark that has the dark photon eventually. So there's going to be actually here a couple stage breaking to make that happen. And in this case, what we find is that we can not only implement this type of scenario, but you can see we can actually get a much richer phenomenology. So I'll talk a little bit about that theory as well. And finally, most recently, we used this lepton portal matter framework as a sort of prototype example for an approach that we had with George Wojcik, Shutian Yu on trying to use reinforcement learning to try to become a standard model, beyond standard model builder. And these are very recent papers, and I hope to describe to you a little bit about our approach there. And as I said, the last topic here I won't discuss, but we're looking more generally at full charge lepton flavor constraints, as well as precision, et cetera, constraints on this lepton portal matter. We don't sort of assume certain preferential couplings to the different generations. Okay, so let's talk a little bit about dark photon models and muon G minus 2. And as I said, this is all if the discrepancy potentially is new to do new physics. Okay, if there is a discrepancy and if it is there, if it's due to new physics. Can this provide a possible resolution? And previously people thought basically no, for good reason. So if you just have the dark photon and nothing mixed, no extra portal matter mixed with the muon, then it's just going to be too small because the kinetic mixing, the vector coupling is just too small. You can also try to mix it with some single lepton portal matter pair, but this is going to be too small. So here I show you an example where we put in a portal matter pair, the capital E, plus or minus with the L or R, and those guys can contribute to muon G minus 2 through loops where we've got the dark photon and the dark Higgs in the interior, and there's a singlet there that's involved to basically generate the dark Higgs mass and to break the dark U1. But this is also just too small. You can work it out and find that it just doesn't do the job. So then what we realized, of course, is that what you need to have is that the new physics, the portal matter, you must couple it to both of the chiralities of the muon. So instead of just, for example, a capital E, that would be the charged lepton singlet portal matter, we also need the doublet. So here we've got the two sets, the capital L and the capital E. And most importantly, what ends up happening is that we can have the L and the E couple to each other via the standard model Higgs. And that's going to be a coupling, which I have in the expression here for the delta A mu. And that's this YLE, for example. Here I say plus because I'm assuming it's the positively charged ones that are most important, but it could be minus or it could be combinations. So it's that coupling that's important. And notice it comes in the ratio of YLE plus divided by Y mu. So as long as this thing is enhanced, you can basically get the type of correction that one's interested in. Okay. And so essentially because it's portal matter, the mixings of these guys with the standard model muon have to go through the dark sector, the dark Higgs. And so therefore they're going to be suppressed. But you can have this larger contribution basically from the capital L and the E, the new physics only. So you can see it has basically nothing to do with anything other than the content of the portal matter that we have, and it doesn't really matter what's the dark matter, etc. So here we just showed this explicitly. You can look at here we plot basically the Yukawa coupling and the masses of these portal matter fields. Here those horizontal lines are bound. So the purple solid line is the current bound on such portal matter states on these masses. And you can see as we go up to future experiments, you can raise that up and see what you can get. And we can see that for some reasonable choice of Yukawa couplings, we can do this job. And let me just comment, it's similar mechanism as sort of other papers that were done before where they've got some U1 prime symmetry that's broken at TeV scale, but it's a very different set of constraints and a parameter space. So we were quite pleased that this worked out. And I can comment a bit on the searching for these types of things. And in particular, one can do these things by searching directly for these portal matter and looking for those signals, as I discussed before. You'd want to get some type of handle on the YLE plus. That's more difficult. But in principle, these things can be tested long-term in future experiments. So let's go on to the second part, just because time is usually quite short, and talk about why do we want to put it into a broader picture. And it's the usual reasons. Instead of just sort of, writing down some U1 charges, it can be useful to try to understand exactly where they arise from. How might we understand different couplings to different generations? And as we'll see in this setup, without imposing a separate family symmetry, we do have the rudimentary pieces of this type of flavor distinguishing that comes from the particular choice of dark gauge group that we picked, which was a SU2A cross SU2B in the dark. So there's still standard model gauge group in our observable, but this is just the dark sector one. We like this one because it had enough structure to do the job. It has some nice symmetry between the A and the B, which we will exploit. And just having a single SU2 or SU2 cross U1, we didn't seem to have enough richness to really achieve the type of goal that we were looking for here. Okay, so here's the model. And let me just say from the get-go that we also put in a global symmetry, a Z2. This turned out to be important, and it's something we're planning to explore and further in future work, which was about trying to violate this, which one would eventually need to do in any case. This helps protect us from possible charged lepton flavor violation constraints. And as you can see, what ends up happening, this is just the dark part. So first we break to a U1 that breaking comes from a scalar field phi, which is a bidoublet under these two SU2s. And then we get the breaking of the U1 dark, essentially, that comes from two separate SU2 triplets, one from the A and one from the B. So a pretty huge Higgs sector. It's rather complicated. We have the usual standard model Higgs. And then as you can see, we have a variety of different fermion type states. Those are the ones in the lower part of this table. We've got one generation of just the usual standard model objects that are completely benign to the dark sector. These are the ones we're going to identify with the electron eventually, because of the fact that first generation constraints with new physics are much stronger than the higher generations. And then we've got various combinations, psi, V, and S, that have various standard model charges, and they also have various dark sector charges here, either bidoublet, a triplet under one of the SU2s, or a pure singlet. And notice the different charges under the Z2 symmetry, which is going to be, it was important. So the other two generations of the standard model leptons, as well as heavier portal matter and heavier just standard vector-like leptons, by that I mean they don't have U1 dark charges at the end of the day, those are going to arise from the breaking of these states. So now, if we go back one step further, I'll just show you that what do we end up getting? We have our usual dark photon and dark Higgs, and then we have a plethora of other heavier things coming from the richness of the dark sector gauge group. So a dark Z boson, for example, which can be important in certain cases, heavier W, type of objects from the SU2 dark gauge groups, and then similarly quite some complicated sets of Higgses as well as our dark Higgs. So notice the scale of all the other additional things is in the TeV, governed by this phi scalar vev that's TeV scale, and then the GeV comes from those triplets. And we minimized the Higgs potential and did all kinds of stuff with that. In fact, in a backup slide, I have all those details if you're interested. But let me just first comment that here, if we go and look at the fermions again, it turns out that because we're going to have, it turns out when we do the symmetry breaking, there's going to be a residual Z2 prime. The Z2 prime is not just the Z2, it's going to be some combination of Z2 and some discrete symmetry remain from the breaking of the SU2 cross SU2 to U1 dark and the breaking of U1 dark. But this Z2 prime symmetry remains, and it means we've got two blocks for the fermions. And one block is positively charged under the Z2 prime. The other one's got the negative. And so they don't mix with each other. And so the lightest state in each block is going to would be zero in the absence of a standard model Higgs VEV, whereas, and then there would be heavier states. And so the lightest one in each block is to be identified with a standard model lepton of either the second or third generation. So let's think about the different possibilities. Basically, we can have two possible scenarios, which we call A and B, as to whether or not the lightest state in one of the two blocks was identified with the muon or the tau. And so if we basically take the Z2 prime symmetry as -1 for the lightest state to be the muon, then that's the scenario A. And as we'll see, this one resembles our minimal model that we just discussed. Or you can have the Z2 prime plus 1, and that's going to be a different scenario that has much more like typical vector-like lepton type of situations. And they're going to couple, for example, to the dark sector gauge bosons. So both can do the G-2. Now we have more possible places to flip the chirality along the lines. I didn't write down the huge Lagrangian here. It's in the backup slides as well. But as you can imagine, Yukawa couplings are labeled just to which things talk to what. So HS, for example, would be, standard model Higgs thing connected to the singlet fields under the singlet in the dark. We've got HV, which is the V objects. And so you can see in scenario A, what happens is that the important things inside the loop are the dark, and the H3 is the Higgs dark here. And so those are more like the standard minimal workable model. Notice here we've got two different possible terms. So there's some interplay as to which one is important. And in scenario B, what we have is instead, that's when it's flipped, which one's the muon and which one's the tau. And now it's a particular coupling instead. And it's the dark sector gauge bosons and the dark Higgses that come in that are heavier, that are becoming, that are important. So just to show in scenario A, we can certainly accommodate either way, whether or not it's what we call the tau mass term dominates or the HV, the other one. And so this is just to sort of show you. Here we also include a perturbative unitarity bound on these Yukawa couplings and some set of parameters. These theta deltas and theta m's have to do with various definitions and rewriting things to make things simpler. We've taken all couplings real here. We do allow relative signs, which actually is important for the G-2. So that shows you the scenario A. In scenario B, basically what ends up happening is there's this one coupling, but there's a variety of different vector-like lepton mass terms that contribute to this. And if you could either have constructive or destructive interference when you sum up the contributions from those different pieces. And it just shows you just get a different range of Yukawas that can sort of do the job for a given heavy portal matter mass, whether you have constructive or destructive interference, but both of them are within the reasonable realms for a reasonable variety of parameter space. So that's the G-2 story. There's actually a pretty long story about collider phenomenology. I'm only going to mention it briefly here. We can have direct production, and we're going to have similar rates for both scenarios. And in our theory, the lightest heavy fermion state is going to be the portal matter in general. So it's going to be the one with the U1 dark charge. And so that's a standard feature. And so that means one's going to get these types of decays. In scenario A, what's going to happen is those guys are going to decay to the muon plus some dark stuff. And that's our usual limits lichen before with the toy model where that's all you had. But suppose we have a situation where maybe kinematics allow us to not only have a decay to the dark photon dark Higgs, but maybe also these dark W bosons, for example. This can happen. And I've shown one example of such a, the plot shows one example of the branching ratio for such a decay as a function of the heavy gauge boson mass for some variety of parameters again. And let me just comment, because of the fact that these things are talking to the muon, this whole scenario is very well suited for exploration of the multi-TeV muon collider. And so we did a number of sort of, potential, speculated possibilities for what such a collider might look like, and how it might probe these types of theories. Now in scenario B, you'd have the same types of processes, except for instead of decaying to muons, it would decay to taus. And so therefore there's weaker limits. It would be harder to see that way. For both cases, you can also have diboson production. You can look at the Higgs sector. We have many more details of that in our paper. And the main point here is that actually it's quite, it's quite a rich phenomenology that, again, is a nice test case for thinking about how you might be able to use a muon collider to probe sort of interesting new physics that couples to the lepton sector. So that's the sort of, again, many more details that I can talk about or show you in our paper. But because I wanted to also talk about our newest work, I'm going to move on now to the last bit of it. Let me just check how I'm doing in terms of the time. I know I'm probably running pretty late. And this is this idea. And I'm going to credit my junior collaborators, George Wojcik, Xutian Yu, for really pushing on this idea and having the vision, pushing me toward, breaking out of a, more conservative box in terms of thinking about particle theory. And that was this idea that maybe we can use reinforcement learning to try to build a automated BSM model builder. And so the idea would be to use this reinforcement learning in part because you don't have to train using some large data set, which is a nice advantage here. Instead, what happens is reinforcement learning kind of at the very basic level, what you have is a state space, and you have an action space and an agent. And there's an agent that explores the environment in your state space, takes some action, and then there's some reward. And if you're rewarded positively, you might want to take an action in the same direction. And if it's not, then you might want to consider a different type of action. And the aim overall is to maximize the cumulative reward. And it's a Markov decision process, so meaning it involves only the current state and not the accumulated history. So that's the basic notion here. And in fact, reinforcement learning has already been used somewhat it's starting to be used more in high energy physics to explore very large parameter spaces. And previous studies show it can identify new points in non-trivially distributed regions of large fixed dimensional spaces. So for example, in string theory landscape, there's a number of interesting papers. But one thing we noticed was that if you wanted to do some sort of model building, you might want to do things like add particles or add things or just take things away or whatever. So you want to change the dimensionality of the space and not have it fixed. So this is the thing that we want to have. We want to have a scenario, a setup where we can accommodate such a situation where the parameter size, space size can be variable. And so the very interesting idea was to use, and again, I credit postdoc George Wojcik in large part for this, was to represent BSM theories as a graph and to use graph neural networks to do this job. And so here's the approach. As long as you have a finite number of fields, so it doesn't accommodate infinity, so no infinite towers, et cetera, yet you specify the symmetry group and which representations can occur, and then we have a graph grammar architecture that we can use. And the graphs have nodes and edges to them. So the nodes can be fields or coupling terms. The edges connect field nodes to coupling nodes. And they're what are called heterogeneous graphs, which means different node types, which have different feature vectors. So each node has some feature vector that describes it. So here's an example. And as I said, we explored this within our recent favorite framework of this lepton portal matter and include vector-like leptons. So if you look at the red table, you'll see not only do we have the L plus minus, E plus and minus as the fields, but also L0 and E0. This is just to say those ones don't have U1 dark charges. So those are more like just standard vector-like leptons. And here's an example of writing a grammar. This is not unique. In fact, we explored different possibilities in our papers. Here, the idea would be there's two different node types, a particle type and a coupling type. So in the particle type, there's these four types of states. And there's a feature vector, which includes their masses, how they couple to the standard model, whether they're electroweak doublets or singlets, and whether or not they have U1 dark charges. And then we also have coupling nodes, and these are the things that couple these different particle nodes together. So notice these are the ones that either couple L and E of the 0 type or the plus or minus type, or they couple the you know, the L plus to the E0 or whatever. So they're basically of those types. Here, if you see a Y, that means it's going to be a coupling that involves standard model Higgs. If it's lambda, it's going to be a coupling that involves the dark Higgs. And then there's different edge types. So how you couple these objects together. And this is just because of the way we have particle physics coupling. So we needed to have two different edge types to connect. And so here's a visualization of this graph. And this is if we have, this particular set of objects. Okay. And so if we want to then go and do the reinforcement learning investigation, first you construct this graph grammar, and then you're going to have to determine what we call a promising model. So a new physics model, of course, has to satisfy specified constraints. So it would have to not violate various experimental constraints, either direct or precision. And it could, for example, you could put on there as a input, which we did for this study, can it accommodate the mu on G minus 2? It could be anything you want. This is just a proof of concept. And then we have to construct the necessary elements for the reinforcement learning process, which is to specify the state space. The action space here, which we'll see is called hybrid. It's hybrid because we have both discrete actions and continuous actions. Continuous actions can mean changing the magnitude, for example, of overall of a Yukawa coupling. And discrete actions can include things like changing the exponent of that coupling, can also include broader discrete actions like deleting a particle, adding in the corresponding changes in other nodes from that. You have to specify a policy that governs the agent's actions. And here we're using what's known as HPPO, hybrid proximal policy gradient, which is an actor-critic structure. And this is a well-known approach in reinforcement learning. And then you have to design the reward function, since what we're trying to do is maximize the cumulative reward. So here we want is to calculate various observables. You want a larger log likelihood for the new physics model than the standard model. And we also want here, we chose this for our study to minimize the number of BSM particles. So not to have too many that are just hanging around not doing anything. And this is just as a starting point. One could change those types of that second part. So here's the types of actions. So you can modify nodes. That includes adding particles, deletings. And if you add the particle and delete, that's going to change which couplings you're going to have. You specify your state space, and here's they are explicitly. And as I said, we're going to emphasize that minimal constructions, the upper limit on the BSM particle number. So there are many more details in our paper about exactly how we did this in details and et cetera, to put it through the graph neural network. Let me just show results here since I'm probably almost out of time. What this found was 6 distinct sets of particles identified, each with 2 BSM particles, so minimal as we were looking for. We labeled them A through F. A and B are just our minimal model that we had before, we have L plus, E plus, or L minus, E minus. The rest of them are quote unquote new. They have one portal matter state and one vector-like lepton. And now what we see is we have a similar type of chiral enhancement possible for the mu on G minus 2, but it's just a little bit different in terms of how it works, because now what happens is the portal matter, whenever the portal matter mixes with anything, whether it's a standard model or the vector-like leptons, it mixes via the dark Higgs. And the vector-like lepton and the standard model mix via the standard model Higgs. But either way, we've got the same types of combinations we had in A and B, even though it's different objects playing different roles. Okay. So we have many, many more details in our long paper, in particular, effects of various what we call reinforcement learning hyperparameters on the agent's performance. This is standard in such scans. I'm new to this field myself, so I'm learning about it myself. But basically, there's various parameters, for example, something called an entropy coefficient. And this is put in the reward function. It's designed to be a trade-off between exploration of where we've already been in the current state. So current region, say, suppose you're going through this process of reinforcement learning and et cetera, you're in some region of parameter space, then you can either keep exploring around there, or you can say, hey, I want to go someplace much further out. And so exploring out versus exploiting the region that you already have. And so there's a parameter that has a pretty large impact as to how it allows you to do that. And that's actually very important for the scans. There's a number of other parameters that are important as well, but this is probably the most important one. There are different ways to configure your hyperparameters. So you either get the largest number of terminal states through some particular number of episodes of this process. Terminal means acceptable models. And there's another set which you can use and to explore where you have the largest number of different model types as opposed to the largest number found. So you might find the same type of model over and over and over again versus lots of different types of models. There's different ways to encode physics information in the graph grammar. Let me just comment that here I only showed one type of graph grammar, but in our paper we explored two. And the main difference between the two was that in one case, we basically let the fact that we had electroweak doublets or singlets either be detailed in the feature vector of a given node, or they would be separate nodes altogether. And so the one I showed you was when they were in the feature vector. So there weren't sort of separate nodes, they were all just particle nodes. But you could take a different graph grammar, which we explored, where basically maybe there would be a certain type of node, different category of node for doublet versus singlet. And it turned out that this one seemed to be less useful. Of course, in retrospect, maybe it was clear why basically the neural network had to learn that this was a double, things were doublets, whereas before we told it. So there's some balance between how much you want to tell this thing to start as a theorist versus not. But let me comment, we allowed all the couplings, including couplings to all the different generations of standard model leptons to just be to float, and we put in various constraints from precision, from flavor, etc. And so it finds these things without us having to say, we didn't have to tell it a priori that it can't couple strongly to the electron, say. It found that out. And so we were pretty happy with this. And even though this is a very simple framework and our study of just getting these minimal scenarios, it may seem like, well, this is a lot of work just to come up with models you could probably think of yourself. This was just meant to be a proof of concept of this type of an approach. And we think an important first step in maybe generalizing this. And the grammar structure and that prescription is something one can in principle apply to any BSM theory as long as you have group specified, representation specified, and a finite number of particles. So we think there's a lot that can be done with this type of approach. Okay, so let me come to the end. To summarize, within this general paradigm of this light dark matter models based on some dark sector, I'm claiming that these lepton portal matter, and in particular these flavored ones where they're coupling preferentially to different generations, is an interesting framework for beyond standard model physics. Phenomenology is quite rich, even in minimal implementations, and it's well suited for muon collider probes. And so, if we're thinking about very far future, hopefully about new types of technology, this could add to the lexicon of reasons why such a thing might be useful to explore to see if such types of states are out there in our physical universe. We also used it as a test case for our approach to basically build a reinforcement learning based BSM model builder. And the key idea was to represent beyond standard model theories as graphs. Those graphs can be put into graph neural networks. And then from there, you can learn through a reinforcement learning, actor-critic structure, maximizing a reward, and you can design your reward based on what type of new physics you're trying to explore. And this one is generalizable, as I said, to a broad class of four-dimensional theories, and there's much work to do to continue this if one is interested in developing such an automated approach. At the very least, it should be complementary, if not replace, the types of standard ways we think about coming up with BSM theories. All right, one final slide is just to say thank you again for the opportunity to be a part of this important celebration of Durmush's life and career. I am truly sorry I can't be there with you in person today. This has been such a difficult loss. Being far away, it was hard to take in. I have thought of him very often, and I'm certain that the way he dedicated his life so enthusiastically to theoretical physics, it inspired so many of us. I saw the statements others of you wrote about him and how much he meant to so many of us in physics. I believe he will keep guiding us as we seek to understand our observable universe, and his own contributions, of course, are a lasting and profound contribution to this journey. Thank you very much.
Thank you very much, Professor. If there's a question, we have maybe time for one question.
And if you could, if you don't mind, repeat it, say it again in the mic, because I was having trouble hearing the questions before. Yes, I'm happy to take any question.
Can you hear me?
Yes, I think so.
Okay. I was going to ask about your last paper, graph reinforcement learning.
Yes.
How much computational power did you need to get those results? Like, was it just an ordinary laptop, or did you use a specialized, maybe
Well,
HP?
we actually used our sort of Condor, we used our departments, mainframe that was used by high energy experimentalists, but I think it was not hugely intensive. It was not something that was such an enormous job that it took a very long time. And a big part of it was maybe the way we designed it. Of course, I think if we wanted to know the details, we sampled 32 parallel environments, and there were a number of 250 steps total to decide whether you came into terminal states or not. And essentially, we repeated all these things over, we had 10 independent initializations each time, and we repeated the experiments 10 times. And so I think overall it was about 1 million models. But, I have to say, being the senior person now, it was my junior people that ran all these codes, but they said it wasn't so bad. It didn't
Yeah.
take that long.
I was wondering, like, if you had any like idea about like as an order of magnitude, how much CPU core hour would be needed for something like this. But I guess it would be
I
hard
think
to.
it very much depend on the type of theory. So you see, what we picked was actually pretty, you know, it wasn't huge. And in fact, we bounded the number of new physics particles that we could have, just again to try to see if things can work without letting it have to. I would imagine the more you allow to be able to add, the larger you would have to do. So, but it's a good question. I should have a better answer to it. But I think for us, for our particular first study proof of concept, it wasn't hugely intensive, but I can imagine it's certainly growing, and that would be something to then figure out how to optimize.
Yeah, thank you so much. I'm just related one small question. So, do
Yes,
you know whether you guys use GPU inference or just CPU?
it was GPU.
GPU inference. Okay, thank you so much.
You're welcome.